Thank you, everybody, for inviting me here. So I think let's start. We're going to go back to a little bit what we saw in the morning regarding a little bit of quantum technology. So it's nothing on the protocol or higher layers. So we're going to deep dive into the physical layer. And I guess I just move myself through the mouse. I have a clicker as well. Yes, so let's start defining what quantum communication is, right? Quantum communication is a field of quantum physics that studies the transfer of information of quantum states between party A and party 2, or even more parties. So, and the goal is to distribute random bits or entangled states or any kind of information that is useful for these two parties. So quantum communication links nodes, right? And this can be quantum nodes. And the most mature application right now of quantum communications is quantum key distribution that you heard this morning. But it's not the only one. There's other applications as well. I also would like to say in this slide that quantum communication is one of the flavors of quantum technologies. You have quantum computing, that you saw also this morning, and you have quantum sensing, for example. So everything started in 2018 when we decided to link the Ericsson lab to the KTH lab. By the way, all you'll see here, it's a collaboration between KTH, Ericsson, and also StuCap. And then we wanted to send qubits between Ericsson and KTH. So StuCap provided the fiber, standard single-mode fiber. We don't need anything special. We don't want anything special. And at that point in time, we actually sent qubit, single photons, which we call qubits nowadays, between KTH to Ericsson and back. And we could detect these single photons. But as you probably know, because you're optical people, the polarization of light is not maintained over the fiber and over long distances. And you need that for quantum communication if you're using the polarization degree of freedom of the light. So if you send a V-polarized photon, you want to receive a V-polarized photon and not the other way around, right? So in order to check how much the polarization would drift, and also to maintain, so we did some studies. You can see here the Stokes vectors of measuring the polarization over a certain amount of time, which is quite flat. Flat means good in this case, because it means that it's stable. And you can also see the drift of the polarization over 30 minutes in the Poincare sphere on that graph over there. So it's quite stable. Then we can stabilize it, meaning that if we send V, we want to receive V. So we went one step further and we said, okay, we've characterized the link. That was done with classical light, laser sources, regular laser sources. But then the step further was like, let's use single photons. And now you're used to think of a pulsed laser of 10 to the whatever, 10 to the 20 photons, right? But now we're talking a single photon. We wanted to send that single photon between KTH and Ericsson and receive it. So for that, we need certain things. One of them, you need the single photon emitter. In this case, we used a quantum dot source, which was produced by KTH, Matthias Hammer's group. And then we used single photon receivers. So these were devices provided by Professor Waltzwiller at KTH. And in this case, we wanted to check the purity of these single photon sources. Let's say we use QKD. Let's say we use a protocol BB84, which uses one photon to send one information, right? You want to make sure that it's only one photon and not two and not three, because if it's three, you can steal one, right? So you want just one photon. So there is a way in physics to measure how pure your single photon source is. In this case is with the G2 function, which is the second order correlation function. And as it says here, right, it gives a measure of how likely it is to find a photon after another one has been issued, right? So in this case, the closer to zero, the better. So if you measure, in this case, we measured 0.176, we could make sure that our photon source is actually a single photon source. And then we also used, as I said, the single photon detectors, because a normal detector will need a certain amount of energy that hits to actually produce a current afterwards, right? So we need special detectors, and usually both these photon sources and detectors sit in a cryogenic space. So in this experiment, we also checked the entanglement. So if we could send two photons that are entangled, because these quantum dot sources, since these are sort of artificial atoms, we could create two photons emitted at the same time that were entangled. Once we checked that we could send and receive, create these single photons, we put information to transfer, because that's at the end of the day what you want to send is the ones and zeros that I'm sending to you, right? You want to send them through the fiber, you want to be able to detect them and decode them. So this is what we did here. We send this pixelated data you see here on the original data. It's the Ericsson logo. And then we used several codes to send this information. And also error correcting on those codes. And those codes were codes that we sort of invented at that time. What you can see here at the top on the received data, in here we used only two code words, V and H, of length 1. And the red pixels means information that has been lost. So here on the first received data, just right beneath the received data letters, you see all the errors that we could detect but not correct. Next to it, you will see after retransmission. So we send it again, the same information, and then it allowed us to actually reduce the number of red pixels. For the second row, we used also two code words, but in this case, they had the length of 3. So the first time we sent the V photon and H photon. This time we sent V, 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 H, 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 and combinations. It's the same, detect and correct, and the next one is with retransmission. Finally, we also use code words, 5 code words where we were able to detect and correct errors. And if you see here, after retransmission, we're able to actually to get back to the original data. So this proves that we can use single photons and single photon receivers, not only for QKD, but actually for transmitting regular information. Don't ask me about the bit rate because it's very slow, but that's another thing. That's for the future. Then we use this link to, for example, distribute random numbers. Let's say we have a central location and you want to distribute random numbers to several clients. So we use these photons, the single photons and the entangled photons, to actually distribute these random numbers. In the first case, so we use two methods. One, we send the photon, and then at the receiver side, you have a beam splitter. So the photon, since it's one, can decide, I go this way or I go that way, right? If it goes this way, it will click in this detector. If it goes that way, it will click on the other detector. And if the power splitter is made, if there's no engineering failures, let's put it this way, it's a 50% probability that goes this direction or that direction. So that makes it totally random. It's like throwing a coin, right? But more in the digital world. So this gave us a number of random numbers, but the rate was not good enough. As you see here, it was 19 kilobit per second. You have to think that regular or the new quantum random number generators are up to speeds towards the gigabit per second. Okay, so we were a little bit far from that. We also used the second method, where we, as I said, we have a quantum dot can emit entangled photons because it's a 3-level system: ground state, first state, exciton, second state by exciton. So by looking into the decays of how they recombine electrons and holes and the photons that get emitted into these recombinations, we could actually also generate random numbers. In this case, we had the higher rate, which was 80 kilobit per second. Yes, it's written here. But it's also for further improvement because, as I mentioned, products out in the market for quantum random number generators up to the gigabit speeds. In a similar setup, we also send these two entangled photons for time synchronization use cases. So we would also send one photon, measure the photon in So the service here would be a central provider of a time, absolute time, that it gets distributed into different clients. And this is comparable to what's the GNSS today, it's over air. So basically we send one of the photons, it was detected, another one stayed at KTH, so one sent to Schista, detected, the other one sent to KTH, but also we detected the back reflections of the one that was sent to actually correlate the measurements. All of these experiments need, as I mentioned, a single photon detector, and this is how it looks like, and it's sort of a device like this, and it comes with also with the pump or the helium compressor to refrigerate the detectors. So this is basically superconducting nanowires, and this device that we have in the lab is from a company called Single Quantum. You have the detectors in the cryogenic, and you see this green box, the gray box over here, which is the helium compressor that cools down the detectors. Because of course now you're detecting single photons, so you want to get rid of your thermal noise, right? Otherwise you won't detect anything. In order to get rid of the thermal noise, you need to cool them down. So basically how it works, you have a superconducting nanowire, and then a photon hits it, right? And it creates a hot spot. This hot spot actually breaks this superconductivity, and it creates a resistance between 2 points, which you can measure as a voltage spike and eventually as a current, right? So this is how this single photon detector works, and they are, as mentioned, they are able to detect at the single photon level. And then, also related to quantum communications, we got some funding to actually build the Swedish national quantum communication infrastructure. And this is what you've heard this morning, what's called the EuroQCI. And this is the initiative that the EU is putting money into for each country in Europe to actually build their infrastructure for, in this case, for QKD applications, quantum key distribution. And this is together with KTH, Chalmers, you can see the consortium here, Quantum Scopes, QCertify, and Linköping and Stockholm University. Why do we do that? I think it was also explained this morning. There is this quantum threat and the Shor's algorithm. If RSA is broken with a quantum computer, we need to have something else. So what is this something else? One of the possibilities, it's quantum key distribution. So let's see how mature it is. Let's build it. Let's make sure that we know how to do it when the time comes. So that's basically, I will not go through that because you've seen this morning. So we bought a couple of devices, one Alice, one Bob, transmitter, receiver. You connect them, they are plug and play, very easy. In this case, we used Lux Quanta devices, which are based in continuous variable quantum key distribution. There's just two techniques. You go for continuous variable or discrete variable. We're going to test the discrete variable later on, beginning of next year. It's a little bit delayed. In any communication link, you want to know the SNR, which in here it depends, is directly proportional to the transmittance and inversely proportional to the excess noise, right? So you measure these things, and at the end you get a key rate. And this is what it's interesting, right? Because the key rate will allow you to secure your messages, which later on will be encrypted with AS256 or whatever you want to use at the upper layer. The devices, some of the findings that we've found so far for this project, of course, the higher the loss in the link, the more Gaussians you need to acquire. You have to think that the continuous variable QKD technology uses an attenuated, a highly attenuated laser. So it uses Gaussians. It doesn't use single photons in this case. So in order to accumulate enough key material, you need to send lots of Gaussians when the loss is very high. So in this case, I think for a loss, so these systems are limited at around 13 dB loss. Longer than that, you will need to go for another technology. But as I mentioned, it's plug and play. You would need also, if you want to go for longer distance, you would need a trusted node where you can repeat the schematics that I mentioned, Alice, Bob, Alice, Bob, Alice, Bob, and concatenate them. And then our next step in this project is to test the DV technology. This is how it looks like, architectural-wise, when you deploy a QKD solution. So you have the physical layer at the bottom where you transmit the qubits. And then you have a KMS system, which is a key management system on top, which stores the keys. It might buffer the keys, and then it gets them ready for the encryption layer, AES 256, for example, you can use here. And these interfaces are also standardized by ETSI. In this case, we're using ETSI 014. And then you can put your application on top, right? In this case, we actually run a Lotto app. So there's a server that has random numbers, and there's a client that has this slot machine. You click, and then you get the random numbers, which are encrypted with QKD. You can come to Ericsson and see it if you're curious. I can show it to you. Good. So I mean, summarizing, right? Quantum communication is only one of the flavors of quantum technologies. As I mentioned, there's a lot of people working on quantum computing as well, and some other people are also in quantum sensing. Also in Sweden, there's different universities that have appointed different areas in quantum technologies. One of the most mature of these applications in quantum communications is QKD. But also, I mean, this QKD is also fueling the development of devices like single photon devices or single photon emitters, single photon receivers, which can be used, as I showed you, for other use cases like transfer of information or time syncing or generating random numbers. And with that, I think I'll thank you for your attention.
Thank you very much. Do we have any questions for Gemma? Question right at the front here, please. Can we have a microphone to this gentleman? Thanks.
Hello, my name is Jonas. So let's see if I can phrase this question. With this QKD, basically what you're doing is that instead of using like Diffie-Hellman for key distribution, you're using the quantum mechanism.
Yeah, correct.
But if you're still using a traditional symmetric crypto, like AES or something, like what have you really gained if that can still be broken by a quantum computer?
No, AES cannot be broken. The EAS 256 is known not to be broken. What can be broken is the RSA, which is the asymmetric encryption protocol. Yes, the AES sits on top of what we do. There's several steps, right, in encrypting or securing a channel, right? So this one protects at the physical layer, how you distribute the keys. Then how you use the keys with your encryption algorithm is another way, right? And AES, it's not known to be broken.
But is it quantum safe?
Define quantum safe, right? I think so. If it's not to be broken right now, I guess you can say it's AES, it's quantum safe. But how you get the keys for the AES 256 might not be quantum safe.
Any more questions?
There was one from Menti. So someone wanted to know, so this is in regards to when you were streaming the random bits. How can the receiver verify that they are cryptographically secure or in other ways high quality?
Yes, it's a good question. I think there is no way nowadays to tell if a random number comes from a Zinner diet, for example, or from a pseudo random number machine or from a quantum random number machine, because the test that NIST has published, which is this SFP 800/ATB tests, only are specified for classical machines, not for quantum machines. So right now there's no metrics on how to measure this quantumness, unfortunately.
Any more questions? Okay, then please join me in thanking Gemma for a fantastic presentation.
Thank you.
Thank you so much.